wave is typically modulated by what's called a phase pattern or a phase-only hologram. And this modulated wave propagates to some distance, and the interference of this wave is what is our image. So in a LCD display, the images are completely ray-based. So we modulate the light rays and its intensity to form an image. Whereas in a holographic display, the images are wave-based. So we have a wave, we modulate the phase of that light wave, and we let the wave propagate to some distance where the interference pattern itself is the image. So as you can imagine, the phase modulation that happens on this light wave directly affects the quality of the holographic images. So there are many methods to compute these phase-only holograms. For example, there are a couple of heuristic methods that were proposed in the past. A popular method is called Gershberg-Saxton, where you propagate the light waves back and forth between a phase modulating plane and a plane where the interference pattern is forming an image. We call this an image plane. So we propagate the light wave back and forth between this hologram plane and the image plane until and enforce certain necessary constraints on either of these planes until a good phase pattern is found. So this kind of approach works reasonably well, but it's kind of extremely noisy because you are heuristically enforcing constraints on this kind of wave propagation. And then there are other widely used methods called double phase amplitude coding method, for example, where you propagate the light wave from the image where you know what image you want. You assume some amount of phase on that light, you propagate it to the hologram plane, and then you do some kind of heuristic encoding of this complex wave into a phase-only amplitude, phase-only hologram. But both these are heuristic methods, and they have severe limitations. They're extremely noisy and stuff like that. So a trivial thing to do is to directly optimize for these phase patterns. Right? How would you do that? You start with some random initial phase pattern. You propagate, you modulate the light wave with some random phase pattern. You propagate this wave, and you compute the intensity on the image plane, and you compare it with the target image that you want, and you back propagate the error into the phase. And you keep doing that multiple times and until you find a good phase pattern that can create your holographic image. But this approach isn't straightforward, and I'll tell you why. So if at all you can use a standard optimizer that can and provide gradients to this optimizer, you should be able to technically optimize a phase-only hologram. Let me make this clear. So let's say you have an initial phase phi. The complex amplitude of the light wave is going to be some amplitude times exponential of this phase, right? And let's call this as your hologram. You let this hologram modulate the incoming light, and this light is propagating through a distance, and let's call that propagation p. Right, and here you are computing the intensity of the wave interference, and let's call that the target as I, and the intensity of the propagated wave, absolute value of z square, where z is the field, the complex light, the complex wave field on the image plane, right? So essentially, you're trying to reduce the error between the target image and the intensity of the light wave at the distance that you want to create the image, and you're trying to optimize for the phase pattern so that your error is minimum, right? So you can use any standard optimizer if at all there is a gradient. And how do you compute these gradients? You can simply compute it using chain rule, where you're propagating you want the gradient of the error, which is some error function f with respect to the phase that you want to optimize. And you basically compute as a chain rule where the overall gradient will be partial of this error function with respect to the wave field, and then the wave field with respect to the hologram, and the hologram with respect to the phase. Here, one important thing that that we want to know is what's called a holomorphic function. Right? A holomorphic function is any complex function that is complex differentiable. So, here we are looking at complex description of a light wave, and so the domain of this error function is a complex function, and any derivative of such a holomorphic function which has a real valued output is always zero, or it doesn't exist. So if you look at this particular term in the chain rule, you have a real valued function, a real valued error function, and you have a complex valued argument, which is the complex light wave description. And so basically, long story short, gradients for optimizing these kind of functions do not exist. So derivative of any order is not defined for this kind of an objective to optimize for phase-only holograms. So here we look at two important properties of a gradient, right? Where a gradient defines the direction of maximum rate of change, and the gradient is zero at stationary points. So we define an approximate gradient definition based on these two important properties of gradient, and then use standard off-the-shelf optimizers like currently these gradients are also built into TensorFlow and PyTorch. These are the popular machine learning libraries. And this allows us to optimize for these accurate phase patterns. So here you see images that are computed on a hardware or a benchtop holographic display. And these images are totally formed by the wave interference pattern. So as I said before, these are completely different from the LCD or LED based displays, which are ray based. These are completely wave based, and you can see on the left, this is like the Gershberg-Saxton method that I described previously, which is completely heuristic, where you're trying to propagate wave back and forth until you hit a reasonable phase pattern. And as you can see, this is like extremely noisy. And this is another kind of heuristic encoding method called double phase amplitude coding, which is again has its own errors. These show ringing artifacts, reduced contrast, and stuff like that. Whereas on the right, you see these holographic images that are obtained with the gradient descent optimization with complex Wittinger derivatives. And these very fine details like the TV lines in this chart are preserved, the text is preserved, and the image is pretty high quality here. And similarly, you see here I show a color holographic image. Again, it's pretty clear that these heuristic encoding methods are like extremely noisy. And then you have these double phase encoding, which is kind of the state of the art, previous state of the art, which has reduced resolution. And here you can see that, these fine resolution, the fine lines are preserved. But again, the images are not perfect. These are nowhere close to what a regular LCD or the current day 4K or Ultra HD image generating displays are achieving, but it's a pretty great progress. And we want these holographic displays to work because if you look at these regular VR displays, for example, you have a VR display panel, you have a lens, and this lens is trying to magnify this VR display. So throw it at a distance, at a distance where the eye can comfortably focus, right? Whereas in a holographic display, you can kind of snap all the optics and the bulk into a single hologram, which can generate a reasonable image. So that's the power of holographic displays. And holographic displays can also generate 3D imagery, which is not trivially possible with the existing AR or VR displays, which are completely LCD or LED based. And the way these displays work for generating 3D objects is that typically a hologram is divided into several smaller sub holograms. So you can treat all of these sub holograms as tiny lenses, right? So if there is parallel light coming that is incident on a lens, this lens is going to create a focus point, right? And based on the focal length of this lens, you will create the focal points at different distances. So now imagine you have tiny lenses. Each lens has a different focal length, and you illuminate this lens with a parallel or a paraxial beam, right? So you create different focal points at different distances in space, and that's exactly how you create a 3D image on a holographic display. So each of this sub hologram, you can treat it as a tiny lens, right? And you are illuminating this hologram, say with parallel beam. Then each of this lens is going to create a focal point at some distance, and these distances can be different, obviously. So you can create these focal points in 3D space. And one good thing is that in a complex hologram, you can just simply overlap all these lenses, and each of these lenses will act independently. So you can create a set of 3D points. And so basically, to create this kind of 3D holograms, we typically do some kind of handcrafted object phase. So each point here needs to be associated with some amount of amplitude and some amount of phase of this light, right? So we handcraft some object phase for this image quality, and then we do a one-step back propagation and encode this complex wave into a phase-only representation on the holographic plane. And so iterative optimization for continuous focus of 3D holograms is a challenging problem, and it hasn't been possible so far. So let me review here some common 3D hologram computation methods, right? So there are point-based methods where every point of the 3D object is treated as a point source emitter, and we let this point source emitter emit light within a certain diffraction cone, and then we compute the hologram based on calculating Euclidean distances or whatever. And on the other hand, you can slice this 3D object into several planes and propagate this light wave onto the SLM, and this might create some amount of continuous focus, but you'll obviously lose the information that are between these slices of a 3D object. And so the most successful approaches so far have used light fields to encode depth and view dependent effects. However, as we all know, light fields do not describe the scene completely. So light fields suffer spatio-angular resolution trade-off. If you want higher angular resolution, you lose spatial resolution and so on. And that also is valid for a light field based hologram. So what we did instead is take this light field and then convert it into a complex wave representation. And a complex wave will have all the characteristics of light field and many more. And then you kind of constrain the evolution of this wave within a volume and optimize for a phase hologram. So it's pretty interesting that a hologram and light field are very closely related. Essentially, a hologram is just a more finer description of a light field, or a light field is a more coarser description of a hologram. And long story short, you can basically go back and forth between a hologram and a light field representation. So to compute a 3D hologram, what we can simply do is compute a RGBD light field, convert it into a wave representation, and then let this wave propagate over a volume. Now you start with any random phase, modulate the wave, let the wave propagate, right? And you constrain this wave evolution within a volume and optimize for the phase hologram. So here I show, how these holographic images can be optimized. And this is a time lapse of this 3D hologram optimization. You can see a far field image here, an intermediate focus and near focus, where the blades are in sharp focus here, and whereas at the far focus, you see the tree branches to be in focus. So here you can notice the change in focus between. I'm not going to go into the details of the previous methods, but long story short, you can see how a single phase hologram can enable 3D focus. Here you can see the focus changing between the tree and the cattails near the pond here. And all of this is obtained, with just a very simple setup where you have a phase-only hologram and an eye or a camera. That's it, without any additional bulky optics. So this enables for really compact displays. But while both the 2D and 3D optimization approaches work really good in simulation, as you can see here, unfortunately, the quality of these images on a display, on a real holographic display, are not nearly comparable. As you can see, there are several artifacts that creep in an experimental display setup. So basically, the problem is, all the approaches that we use for computing a complex hologram, all these approaches implicitly make some simplifying assumptions of the display itself. Like, we have perfect collimation at a lens, or, the wave propagation is ideal, the SLMs or the phase modulation is continuous, and so on. And if real world was ideal, then we would be generating images that are ultra high resolution. Essentially, in a hologram, as I said, a holographic display is completely wave based, right? So for a wave, because it's continuous, there's no concept of pixel or a resolution. So theoretically, you can get infinite resolution using a holographic image. But if that would have happened only if the real world is completely ideal. So unfortunately, a real display or a real world has several non-idealities, such as, we assume a perfect collimation, but real world, you might not get perfect collimation. The illumination might be non-uniform. The lenses that you use might have scratches. The phase modulators that you use might be discrete and non-linear. The lenses can have, chromatic, and all sorts of aberrations. And the wave propagation methods that we use might also not be ideal for the real world case. So all of these deviations combined make the image extremely noisy that is coming out of a hardware display. So as a result, when we show a hologram on a real display, these holograms show severe artifacts because of the underlying non-idealities in the real world wave propagation. And this is both unknown and it severely deviates from ideal wave propagation. And the thing is, in real world, even if there is a speck of dust or some kind of turbulence in the environment, the light wave evolution or the propagation might change. To characterize the exact propagation at any instant is a very challenging task. So since this wave propagation model is unknown, one way to compensate for these real world aberrations is to optimize for images that are coming directly out of the display. So for this, instead of simulating these reconstructions and optimizing for the reconstructions, we can optimize for a phase hologram by using the images that are directly captured from a display, and use these images that are captured for optimizing for these phase holograms, in a camera in the loop fashion. But unfortunately, although this approach can eliminate many artifacts, this is slow, because you always have to place a camera to optimize for these holograms, and it's impractical, especially for a near eye display, where it's like you want to share the time between your eye and the camera, and that's that's an impractical thing to do. And also having a high resolution camera that sees the image exactly as the way the eyes see these images, that increases the bulk of the system undesirably. And we are again back to the existing bulky setups. We want this to be as compact as possible. So one way to do it is, okay, you can characterize all the real world aberrations and all the real world problems, and then use these calibrated parameters to optimize for phase holograms. So this is, although it doesn't work well as an active camera in the loop, it can suppress many real world artifacts. But unfortunately, even this kind of a method requires identifying and calibrating all individual sources of errors in a real holographic display. And again, it is challenging to calibrate all sources of errors. And this approach is also kind of fundamentally limited by all the errors that we can calibrate within a display system. So one way to overcome this challenge is, or these limitations is, to learn the entire real world wave propagation using something like a deep neural network, right? So to review, we started with some random phase, and then we let the light be modulated with this phase. The light wave propagates, it creates an image, and we use this image to minimize the error between this image and the target. So in the optimization loop, right? And for this to happen, we need an active camera in the loop, and we need an active display in the loop. So instead, what we can do is we can replace both the display and camera with a deep neural network and try to learn the entire real world wave propagation within a holographic display. So essentially what we are trying to do is, we are approximating a display and a camera setup completely with a neural network. Using then you can use this neural network as the real hardware and optimize for the phase hologram, and that's exactly what I'm showing here. So here you can see a regular holographic image with what's called a zero order. These are all the aberrations that are coming from the practical setup, and with the method that I just described, you can eliminate all these artifacts. I don't know if due to compression, if the images are coming through properly, but here you see a grid of dots like this. This is the target image, and the green overlay that you see here is due to the non-idealities in the hardware, and this is something that is inevitable. It is present in all displays. This arises due to the fill factor of the pixels on the LCOS SLM. Whereas here, you can completely eliminate these kind of artifacts. You can see that the images have ringing artifacts here. Those are gone. The images become sharp. The resolution improves, and the black levels become black. So one of the difficult challenges in any display, for that matter, and especially for a wave-based display, is to create absolutely dark regions. So if you want to create a night sky with the stars, with some stars and say a moon, that's an absolute difficulty to create in a holographic display. And like with this kind of a learned hardware in the loop, we can create images that are extremely high resolution and super high fidelity. So again, here you see images that are coming from the previous methods, and you can see that many errors like these ringing artifacts are eliminated. The black levels, I don't know how well the compression artifacts are, or how bad the compression artifacts are, but you can see that the black levels are absolutely black. And these are pretty difficult images to capture from a hologram. Again, here I show a video that is captured live on our display with this learned hardware in the loop algorithm, and you can see that with the previous state-of-the-art methods, these background which are supposed to be dark can almost never be achieved, and there are these strange ringing artifacts around the Yoda character, whereas here you can see that these effects like smoke, fog, mist, and dark sky, these can be well achieved with this kind of a learned hardware in the loop. And here I show another video that's captured live. You can see how the peacock feathers are very clearly revealed, the improvement in overall contrast of the image, and these are all captured live from the holographic display. So far I've talked about how do we achieve compact holographic displays and with high quality. And so I've described this Whittinger optimization for 2D phase holograms, for 3D phase holograms, and then a learned hardware in the loop for compensating real world non-idealities. So now I'll talk about 3D eye tracking now. So as I said before, as we reviewed, for a normal eye, the eye crystalline lens changes its power and the eyes roll to different objects, right? And I said that the divergence and accommodation, they go hand in hand. So at any given time for a person with normal vision, the divergence distance and the accommodation distance, they are neurologically coupled, right? And so, for a person with normal vision, so if you're able to track just the gaze of the eye, so gaze is where the eye is directly looking at. If you just track the gaze of the eye, you can triangulate it, and you can measure the divergence distance and the accommodation distance. So what this means is just gaze tracking is enough to exactly know where the user is focusing at and on what object, right? But whereas if you have, say a user with presbyopia, right? We've said that, people over 40 years of age will lose their lens plasticity. So they are only able to focus at one particular distance, right? So what this means is, let's say, the user wants to look at the house here. This presbyopic user will try to focus or roll the eyes towards the house, but their lens doesn't change the focal power. So their lens are always focused at one particular distance, right? When you're trying to do gaze tracking for a user who has lost their lens accommodation power, just tracking gaze is not sufficient, because as you can see here, your gaze tracking and triangulation will only give you the divergence distance, whereas at any given instant the user is only focused at one particular distance. Their lens is focused at only one distance, whereas their eyes are rolling arbitrarily. And so this doesn't give a full description of where the user wants to look at and where the user is looking, right? Here, the user is wanting to look at the house, but the user is only focused at the tree here because of presbyopia. And for tracking, the gaze and accommodation of such kind of users, we need more complicated systems like, say, an autorefractor, which is only medical grade, right? Where these autorefractors are used to judge the lens accommodation power. And of course, these autorefractors are the machinery you see in a typical with an ophthalmologist who is trying to judge if you have any prescription power, or if you have lost and if you have any refractive errors, right? So to be able to precisely judge both the divergence and accommodation, which becomes very important for a VR display, because if you want a virtual tag to show, as I've shown in the very beginning of the talk, you want the virtual images to be spatially registered with real world. So let's say you want to have a virtual tag at the house. Even if you present a virtual tag at the house, the user will not be able to look at, because the user is only focused at this distance. So you want to be able to change or adjust for the user prescription. And for that, you need to know precisely where the user is currently wanting to look at and where the user is currently looking at, so that you can adjust for that missing prescription. So to make an eye tracker that can judge both divergence and accommodation distance robustly, we need to first look at how images are formed in an eye, right? So let's say the eye is looking at a far object. So the light rays coming from this far object are focused by the eye crystalline lens onto the retina, where there are photoreceptors, right? Now, if the eye is wanting to look at a near object, the lens changes its focal power to bring this object into sharp focus on the retina, right? So the crystalline lens is changing its shape to bring different objects of real world into focus. But here, one of the good things happen. So fortunately or unfortunately, our eyes are one of the most imperfect optical systems that you can ever find. So, the optics is not very efficient. The lenses and the cornea, these do not have 100% transmission. There's always some amount of light or some portion of light that is reflected at every interface. So what this means is, let's say there's a light ray that is entering the eye. Then this light ray gets refracted at the cornea, the front surface of the cornea, the back surface of the cornea, and then it hits the eye crystalline lens, refracts at the front surface and refracts at the back surface of the crystalline lens. And because every optical interface within an eye is imperfect, there is some portion of light that gets reflected at every interface. And these reflections are called Purkinje images. So here you can see on the right, these faint reflections that are actually coming from the eye imperfections. So, a cornea is a very thin surface, the anterior and posterior cornea. So, the light that is reflected at these two interfaces, they kind of closely overlap. So here you see the Purkinje reflection 1 and 2 from the cornea. And the Purkinje reflections 3 and 4 are coming from the anterior and posterior, the front and back surface of the eye lens. And those reflections you can see here. So the interesting thing is the cornea the cornea doesn't change any shape. So it's always constant. So that means that, these first and second reflections, they are more or less constant and they don't change spatially. Whereas when the eye is trying to focus at near and far distances, as I said, the crystalline lens is changing its focal power. So thereby it's changing its shape. And because the crystalline lens is changing its shape, the reflections from front and back surface of this lens are going to be different for different focal distances. And that is precisely what we explored. So here, if you can see, there is the third reflection here and the fourth reflection here. These two reflections are coming from the front and back surface of the lens. And these are the first two reflections from the cornea. And here I'm trying to change focus from near to far distances, right? And as you can see, these reflections from the crystalline lens changes its spatial location within the pupil. And this is extremely crucial information, right? If you can precisely know where these reflections are in the pupil, you can judge where the user's lens is focused at, or the way the user's accommodation distance is. And you can, using any existing method, you can simply track the gaze with existing gaze trackers. So to do this, we've built a system which is of eyeglasses form factor. And we've we've had like very high fidelity simulation of a human eye. And on top you see a real human eye, and in the bottom you see a simulation where the position of light source is matched between the real experiment and the simulation, and you can see the reflections pretty closely match. So we created a simulation engine where the eye's crystalline lens is modeled pretty robustly, and this matches with the real experiment. Such that at any given instant, we are able to track these higher order reflections from the eye's crystalline lens. And we use those reflections via a neural network to precisely judge the 3D gaze of the user. So with this kind of eye tracking, at any given instant, you can know the exact pupil opening of the user, the vergence distance, so where the user is trying to roll their eyes, and the accommodation distance, that is where the user is trying to focus it, and to what distance are their eyes, the user's crystalline lenses are focused at. So we get the 3D gaze information. And here I'm showing the error plots of vergence and accommodation estimates for a user. Like I want to point that the existing commercial eye trackers, they typically achieve vergence estimation errors that are close to 1 degree. Right? And a 1 degree error in angle translates to a few meters at large distance. So that means, if you judge that there's a car at 5 meters, if the gaze tracker was off by, even like half a degree, you are looking at, couple of, maybe like a half meter error in judging the user's accommodation. So it's very important to achieve an error of at least under 0.5 degrees for future AR glasses to be robust, right? And here you can see that we achieve pretty robust accommodation focal depth estimates, where if the user is trying to focus at 40 centimeter distance, for example, our eye tracker is able to estimate pretty closely the accommodation distance. And here I show the network prediction results that are fine-tuned over different features. All the existing trackers use the images of the eye, the pupil, and the first and second reflections, which are generally called PCCR, or corneal glint based eye trackers. This is the most popular eye trackers that you will find in any commercial VR display. And these kind of become more difficult to handle with AR displays, but these are the trackers that you'll find with in all commercial displays. Whereas now, by adding these additional Purkinje reflections from the crystalline lens, we are able to achieve an angle error that is around like 0.3 degrees, which is like pretty robust. Whereas with depth estimate, it's only a 1 centimeter average error across different distances. And and the average angle error that we can estimate is around half a degree, which is theoretically a good value for robust AR gaze tracking. So here the idea basically is, okay, instead of just using the eye images and pupil tracking, you use these additional information that you exploit from the imperfections within the eye to do a more robust gaze tracking that at any given time will give you the exact 3D position of where the user is looking at. Now, once we have the position of like the depth where the user is looking at, now we can provide prescription support within a AR display. So again, revisiting the vergence and accommodation distance, in a normal user with normal vision, this vergence and accommodation, these are neurologically coupled. So if the user is trying to look at, say, a house, then their eyes are rolled towards the house, and the eye crystalline lens is focused to the house. So as you can see here, if the user is focused at far distance, only the house is in focus and the others go out of focus. And if the user is focused at mid distance, the tree is in focus and the others are out of focus. And obviously for close distance, the book here is in focus and the other objects at mid and far distance will go out of focus. Whereas for a presbyopic user, this becomes very tricky here, right? So for a presbyopic user, as I said, the eye lens is only focused at one distance. Let's say, this is the distance at which the presbyope is focused at. But when the user wants to look at the house, he won't see the house is still blurry because the eye lens is not focused on the house. So the retina is not receiving. The retina doesn't receive a sharp image of the eye of the house. So the house is out of focus. The book is obviously out of focus. But interestingly, the user's eye is always focused at the tree, at the mid distance where the tree is. And when the user's eye is rolling, he'll start to see double images. So when the user is trying to look at far distance, he actually sees the double image of the tree. When the user is at mid focus, then he'll see a tree sharply. And when he is trying to look at close distances, he'll again see a double image of the tree. And to overcome this, people generally use either reading glasses or long distance glasses. So, to be able to read a book, you put on the reading glasses. And then if you're looking at far distances, you remove the reading glasses. And some presbyopes who cannot also focus at very far distances, they'll maybe have to wear, something like a bifocal lens or a trifocal lens. So it's a pretty awkward requirement, especially for, AR use cases. And, one might argue that on top of these AR glasses, maybe, you can put an additional lens, or you can wear your regular eyeglasses so that, you can bring these different objects into focus. But, if you have an AR glasses in eyeglasses style form factor already, and one needs to wear prescription glasses on top of it for better vision, one could argue that, it might be an awkward requirement, but maybe, you live with it just by adding a snap-on slot for these additional lenses. But, what about people who are using bifocal or trifocal lenses? For this, it becomes a very awkward requirement because, like, say, somebody is wearing a trifocal lens. The field of view within which the user can see an image is very limited, right? So, the user can look at the book only within or near objects only within this field of view, mid objects only within this field of view, and far objects only within that field of view. And then the user will have to constantly tilt their heads up and down to bring these different objects into focus. And this is something that I think all faculty here might have been experiencing. So what we intend is AR glasses that can automatically adjust focal power wherever the user is trying to look at, because we have a robust 3D gaze tracking, and the user needs to be able to look at these different objects within the entire field of view. That's what we intend. So let us suppose, we have cracked the solution for the ultimate virtual display, which produces content that is indistinguishable from the real world. We need to think if it caters to all users here, right? So let's say, for people with normal vision, we have a well-focused real world. So both real and virtual imagery are focused. That's good. And people with near or far-sightedness, they'll have some difficulty in viewing the imagery, but will have a well-focused view of both real and virtual objects if they wear a prescription lens. Like I am a nearsighted person, so I wear prescription lens to be able to look at far distances. And for me, if I'm going to wear AR glasses as well, I can have a AR glass on top, or AR glasses, with corresponding or appropriate prescription lenses, and that should be okay. But the problem is with people over 40 years of age, right? These people would have lost significant amount of their accommodation. So, they will have to use multifocal prescription lenses like bifocals or trifocals. And these will cause uncomfortable AR experience because, as I just said, they have limited field of view per every depth range, and they have this awkward requirement of tilting their head to bring different fields, different objects into focus. So here are some numbers. Like more than 50% of US population currently has some or the other vision related problems, and about 40% of the US population here is presbyopic. And at least 40% of the adults here are either nearsighted or farsighted or astigmatic. So essentially, a large population that are going to be tomorrow, consumers of tomorrow's AR displays are facing some or the other vision related problem currently, right? So what do people actually need, right? A person with normal vision, he needs no correction for real world because, he can look at different distances or different objects in real world pretty comfortably. Whereas the AR display, or the internal display as I call here, the AR display should show dynamic correction. Either the AR display need to show images in 3D depth that are spatially registered, or it shows dynamic correction, something like a variable focus display. Whereas a person with nearsighted or farsighted, he or she needs some amount of static correction, just like the prescription lenses that we wear generally. And they need dynamic correction for the AR display because, the display needs to be able to show images across the entire visible depth range. Whereas a presbyopic user, he or she needs dynamic correction for real world viewing because, they currently the old population, they have to use reading glasses or far distance focus glasses. So for these users, we need glasses that can help them look at the real world continuously with the full field of view and having good focus. Whereas for an internal display, they just need static correction. So if a presbyopic user's focus is fixed at, say, 4-meter distance, it's sufficient to show AR images only at 4-meter distance because their eyes cannot process anything further. But whereas for real world, you need this dynamic correction for them to be able to look at different distances. So executive summary is every person who wants to use AR glasses in the future needs some form of correction, either internal or either the AR virtual image correction or corrections for viewing the real world. And we are going to have this like really major advantage with future AR glasses, because we have this onboard compute. There are already a plethora of sensors on all existing displays. There will be like multiple of these sensors which are both outward looking like cameras and inward looking, something like gaze trackers and proximity sensors and trackers. And with 3D eye tracking and depth sensing, we can basically determine where the user's scene of interest or where the user is trying to look at, and correct the vision for a well-focused view of both real world as well as the virtual images. And we are going to have these multiple trackers. So, tomorrow, if the displays are also compact, these displays are going to enable, something like 20/20 vision for all with AR display glasses. And sometimes it might even be more beneficial than your normal vision. So we have a great opportunity here to achieve a dynamic prescription correcting AR glasses that you can wear with or without virtual imagery and get try to get 20/20 vision for all ages. So to give you some context here, let's say, on the left, you have a young Marie Curie who has normal vision, and you have Ben Franklin, who is a presbyope. So Ben Franklin is regarded as the person who has invented bifocal lenses, and that has happened, I think at least a century ago. So within this time span, in the last 100 years, there hasn't been much innovation on how to help users view at different distances with sharp focus, or how to maintain 20/20 vision for all users. So a young Marie Curie needs adjustable focus, internal display to be able to view virtual content. And you know where the user is looking. Now you can adjust the focus of internal display to match that distance. And then, she has a good view of both real and virtual imagery. Whereas an old Ben Franklin, he needs focus adjustment for viewing real world as opposed to the virtual objects. So if we know where the user wants to fixate, then we can estimate the eye lens power with the 3D tracking that I described. And then we can automatically adjust focus for real and virtual world or virtual imagery together. So, general focus supporting AR displays, it can be broadly categorized into, something like providing dynamic focus depth, providing dynamic real world correction, and a wide field of view. And we want simple optics, and, we want it to be computationally less expensive, but something like a holographic display or even a variable focus display. They are just like slightly expensive computationally, but we are able to achieve a dynamic focus depth for virtual images, dynamic real world correction, wide field of view, and it's simple optics. So here I show a prototype display where we used tunable focus lenses for real world prescription correction, and a deformable beam splitter membrane that that is changing the focus for the virtual objects. So here, let's say the old Ben Franklin is only able to look at a very far distance of 7 meters, as I show here, right? So the existing AR displays, for near focus, for a presbyopic user like Ben Franklin, he wouldn't be able to look at an object that is at near focus because, his focus is fixated at 7 meters. So existing AR displays doesn't work for him. Whereas if you have this, the continuous focus adjustment or the external prescription adjustment, you can get the image to be in sharp focus. So here, you can see in the inset that the stamp here is in focus, and the bunny here is in focus. These are the insets that I show from here. Whereas on existing displays, these are out of focus. And similar is the case with mid focus and far focus as well. So for example, with far focus, let's say, we have a bike at 5 meter distance. An old person would still not be able to look at this object, both real and virtual objects, in sharp focus, because he cannot focus at 5 meters. His focus is fixed at 7 meters. Whereas with dynamic correction, you can see that both in near, mid, and far focus, you can always have a very sharp view of both real and virtual images. So, it's like, towards achieving 20/20 vision for people with, even over 40 years of age. So, if we put together these 3 things that I've described, a holographic display that is able to generate images in a eyeglasses style compact form factor, but the algorithms that I described, will help generate virtual holographic images, which are, high in resolution, and an eye tracker, the 3D eye tracking that I described, in combination with the prescription, the dynamic prescription adjustments. So now when the user is changing focus, it's from, say, a near distance to a far distance, the 3D holographic display can render images at far distance. The eye tracker can measure where the user is trying to focus at, and we can do external focus adjustments using this autofocus, the tunable lenses that I described. And so, now the near distance catalog is out of focus, the virtual tags appear out of focus, and at far distance, the images are all clear and the virtual tags are all clear, as opposed to the very first case that we started, which are the current day existing displays. So we see that with these 3 components, if a user changes gaze, these 3 components kind of work in tandem, providing sharp focused images, for both real and virtual objects. And these are the kind of things that we want for future AR glasses. So I mean, like, this is of course not the end of it. We have a long way to go. Like, for example, for holographic phase retrieval, we need that to be in real time. We need to incorporate spatiotemporal and perceptual aspects of human vision, where human visual system is kind of sensitive to certain kinds of contrast and not so sensitive to certain other kinds of contrast. And foveated vision, that's something that we'll have to explore to reduce the compute. And then we need self-calibrating eye tracker. Every person here who is wearing eyeglasses might have experienced this at some point, that your eyeglasses kind of slip over your nose bridge, right? And based on the slippage, your tracking measurements are off, because the cameras that are looking at your eye are now in a different frame of reference, whereas they are calibrated for a particular position of the cameras relative to your eye, and so the gaze estimates will be off. And so we need a self-calibrating eye tracker. We need more compact tunable lenses, exhaustive perceptual studies. If everything has come through, then we need really exhaustive perceptual studies to actually validate what are all the things that we need for future AR displays and VR displays. And eventually we need to move towards like miniaturization of hardware and integration into everyday prescription, like everyday eyeglasses, or maybe something like sunglasses. So we have a long way to go, but I hope I've convinced that having these three components, holographic image generation, 3D eye tracking, and autofocus AR glasses, these three components are important for achieving everyday use eyeglasses. And with here, I end here, and I'll take some questions.
Thank you, Dr. Praneeth, and a very insightful talk. And I'm glad that now this future technology is trying to solve some very important social problems. There are many questions. Due to shortage of time, we can attend few questions. Let me start with now one simple question. You mentioned about the perceptual studies.
Mm-hmm.
And I thought perceptual studies in vision is very exhaustive already. And what specific perceptual studies are needed for any of the topics what you mentioned over here? I mean, perceptual studies, I mean the psychophysical studies. So psychophysical studies, yeah, that are already exhaustive. So what else is needed at this point of time?
So far, people have studied, something like, say, depth perception. How well can users perceive depth, or how well can we perceive images when it comes to, say, foveated vision, right? Or the flicker fusion and stuff like that. But we still are not very familiar on, let's say, the eye saccades, right? And when the eye is saccading, there is a visual suppression. So when the eye moves, for those 10 milliseconds or so, there is no visual perception that's happening within the brain. Right. Now, how can we leverage that into, say, doing something like redirected walking in VR, or or estimating this saccade landing position, so that you can already make your image appear better for the next gaze position if you're trying to exploit foveated vision. And at this point, we are also not very clear on how exactly is contrast being perceived in both fovea and periphery, right? So in foveal vision, we are very sensitive to resolution, whereas in peripheral vision, we are very sensitive to low frequency fluctuations, right? So imagine there's a light in the peripheral vision, which is just flickering with very low intensity modulation, or very, very low flicker. Our foveal vision will not be able to perceive it, whereas our peripheral vision will be able to perceive it, and that results in a saccade change. So can we leverage these kind of perceptual aspects into, say, if you're building a third-person VR shooting game, for example, right? Or some kind of redirected, exploration. Then can we use these kind of subtle gaze change or subtle gaze direction features to kind of let the user explore the interesting aspects? Let's say you create a 3D or a VR movie, right? So in a VR movie, you are free to explore wherever you want, but you want the user to have a particular experience. You want the user to look at, I don't know, say a tiger or a black panther that you've created. How can you redirect the user's gaze without really breaking the immersion with these kind of subtle gaze changes? So if there is a low frequency fluctuation, for example, maybe the foveal visual system, the foveal processing is not very descriptive of that. But whereas, your human visual system is trying to initiate a saccade. So can we change the gaze direction, or can we leverage flicker fusion to generate better or good looking images? So there are these kind of aspects that that I think we still need to explore.
Okay, good. Thank you. So let us look at a couple of questions from the audience. One of the audience is asking for what is the pixel resolution which is needed from the normal eye. What is the pixel resolution and at the foveal level? Probably yeah. And what is the resolution at this stage our display is offering, and where do we have to go? Where this holographic displays will offer? What is going to be the gap?
Okay, yeah, that's a pretty good question. And this thing I think is reasonably well established as to how much cycles per degree we need. There's a little bit of debate between 30 to 60 cycles per degree, but obviously higher the better. And there's also been some studies which say that maybe something like 60 cycles per degree is pretty good for foveal vision. But even at a very high resolution for natural images with some slight variation in contrast, the foveal vision will be able to still perceive it, even despite having a very high resolution in the fovea. When it comes to holographic displays, as I said, it's a continuous wave-based display. So theoretically, we have infinite resolution.
Right.
But the problem is, the current hardware devices, they are not like perfect. So these images have the holographic images have problems like noise that is coming from either the algorithms or even the hardware. And currently the hardware is still in its nascent stages, I'd say. So we have a long way to go. But if in case we have a perfect holographic display, then we'll have a pretty high resolution, because
Okay, good, thank you. And there is another question: can we use these glasses in low light condition?
Yes, that's another very important requirement for AR glasses. It's a very good question, because the existing AR glasses, if you look at HoloLens or Magic Leap or any AR glasses for that matter, the brightness that these glasses can provide is not so high. So we generally use these visors to kind of do that brightness enhancement in terms of perception. And there are also problems like occlusion and stuff that I won't get into. Whereas a holographic display, it's currently mostly laser based. So we can go to pretty bright conditions as long as we are within the eye safe range.
Okay.
But I don't think at this point I'm qualified to comment on what kind of brightness would be sufficient, because on a very bright sunny day, if you want to match that kind of sunlight, you want to tweak the laser power so high. You don't want to tweak the laser power so that it burns your retina. But whereas for low light conditions, I think all AR displays are pretty good, because in low light, the existing AR displays, especially to start with, they don't provide a lot of brightness. right? So with low light, they are pretty good actually. All problems come when we want to have these displays work in bright sunlight. that is the major issue.
Yeah.
Yeah.
Okay, thank you. So there is one more question. How many reflections we expect for a normal vision eye recording a image? So we are talking about reflection 1, reflection 2, reflection 3 when you're talking about the eye tracking.
Right.
So uh, he is asking how many such reflections can we expect? Is there any
So,
more reflections other than the third one, or no?
so essentially all these reflections are happening whenever, so when a light ray is entering the eye and moving towards the retina before it reaches the photoreceptor, any interface that the light ray encounters, there is a reflection,
Right.
because the interface is not absolutely transmissive.
Okay.
So there is one reflection at the front surface of cornea, there's one reflection at the back surface of cornea, there's one at the front surface of eye lens, there's one from the back surface of eye lens.
Okay.
There are also reflections that happen from the retina itself,
Okay.
but these are extremely faint that you need to be very precise, but that's how people do fundus imaging, or even the autorefractor that I described, right? So this autorefractor measures the eye prescription, and the way it does is it shoots a laser pulse or some wave into the eye, and it looks at the reflected wave,
Okay.
and based on the wave, the phase change, or the wave modulation, it judges what is the the lens prescription in the eye. So essentially there are mostly like 5 major reflections, 2 at the cornea, 2 at the lens, and 1 from the retina.
Okay.
Yeah, but the retina reflection is so faint. The things that are um, that are very evident and can be useful are these 4 reflections from the cornea and the lens.
Oh, okay.
Yeah.
All right. So there are more questions, but due to shortage of time, we can answer those questions offline, maybe in the YouTube chat boxes and all those things. So with that, I thank you very much for your very insightful talk and the answers for various questions. On behalf of XTIC, Experiential Technology Innovation Center at IIT Madras, as a part of the IoE CoE, Virtual Reality and Haptics. I thank you so much. And we look forward now long associations and interactions with you in the coming days. We will have a separate meeting. Probably we will schedule sometime in the coming days. A lot of our colleagues now wants to interact with you, and we will talk about some projects to take it forward. Okay, thank you so much.
Thank you so
For
much.
yeah, for the audience, and I have an announcement. Um, this XTIC, Experiential Technology Innovation Center, is Center for Innovations in VR and Haptics at IIT Madras, is going to announce several other new events in the coming days. Please keep a look at keep an eye on the the website. The website is xtic.org. Yeah, we also have this consortium for virtual reality and augmented reality environments or engineering in India. That's a unique consortium in India, bringing all the stakeholders for virtual reality and augmented reality engineering and together along with industries to make a big impact. So if you have not signed it, please look at the xtic.org website and then sign up for the consortium, and we will announce you the next event very shortly. And there are some training events coming up. There are other webinars coming up in the next few weeks. So with that, we will close this webinar, and thank you everybody, audience, for patient listening, and we look forward for the next webinar very shortly. Thank you so much. Take care. Stay safe. Bye. Bye, everybody.